right, I think we should be live. Yep. I guess let me double check that. Yep, looks like we are in fact live. Alright. Okay, so we made it, y'all. First week back after a very long stretch of several weeks without any streaming. So we are back, and we planned on Monday. We planned on basically going through and reading a series of blog posts by Jack Vanlightly. Very interesting. Just overall, his blog is, if you're interested in distributed systems, it's definitely a place to visit often. Lots of high quality posts to look at. And so his latest, he has a series of articles. The last 4 of them are part of a series called Coordinated Progress. It's all about basically orchestration and the idea of durable computation or durable execution engines. And so that's what we've been doing all this week. This is the last one that we'll go over this evening. Every single one of them has been really good so far. I'm anticipating that this will be a good, nice overall conclusion to the series. So I guess let's just jump right in and let's see how we end this. Okay, Coordinated Progress, Part 4, a loose decision framework. Okay. In this last post, we'll review the mental framework and think about how that can translate to a decision framework. Reliability and execution models. Microservices, functions, stream processors, and AI agents represent nodes in our graph. An incoming edge represents a trigger of work in the node, and the node must do the work reliably. I've been using the term reliable progress, but I might have used durable execution if it hadn't already been used to define a specific type of tool. In this slide, stream processors like Flink and Kafka streams are particularly interesting. They've had durable execution built in from the start. The model assumes that processing logic is applied to an ordered durable log of events. Progress is explicitly tracked through durable checkpoints or changelogs. Failures are expected and routinely recovered from. Many of the promises of durable execution are simply native assumptions in a stream processing world. Yeah, I think that's a pretty accurate statement here. I don't think I don't have much more to add to that except for, in stream processing, you definitely have, there is stream processing where you can have operators or nodes that are stateless, but from an overall computing model, um, checkpoints, or just the idea of persisting different stages of computation has been, it's kind of core to the model. You can think of stream processors as always-on orchestrators for data in motion. The durable trigger is the event log itself. The progressible work is defined through operators, keyed state and fault-tolerant state backends. This makes stream processing a powerful production-tested example of how durable execution, reliable progress can be built into the foundation of an execution model. Microservices and functions have not historically had a durable execution, reliable progress foundation built into its execution model, except maybe for some actor frameworks. Reliable triggers exist in the form of queues and event streams, but progressible work has been limited to idempotency. Yes. The durable execution category aims to close this reliable progress gap for microservices and functions. It can provide an additional reliable trigger in the form of reliable RPC and provides progressible work by durably persisting all progress with resume functionality. And basically all of that is to say that as these SDKs or framework, these durable execution engines or middleware, whatever you want to call them, their goal really is to contain whatever source of non-determinism you have in your code, so that, in the case of failures, where you basically want to be able to resume the execution of a particular invocation, you can basically replay the work that has already been done. And you can do that because you can expect that for the same input you will have the same progression through the through the execution, because you've been able to basically encapsulate or capture all the sources of non-determinism. So for example, if you've generated a random, that's like the simple and I guess contrived maybe example that you can just kind of use, which is, whenever somebody makes an HTTP request or somebody makes a call to fetch data from the file system, or when you request a random generated number, the output of that needs to be persisted so that during replay and when you call the same functions, you're not, especially, it's very obvious that, during replay, you don't want the call to generating the random number to run in such a way that it basically yields a different random number than the original function execution, because now all bets are off, right? Because there's probably computation that depends on that random number, hence why you needed it, right? Supposedly. And so if during replay you end up generating a different random number, then any talk of determinism is basically out of the picture. Now, though we should be careful to also say that defining what non-determinism or determinism is can also be application specific or use case or implementation specific, right? For whatever reason, it may be that actually it doesn't matter that the random uh, that the random number that's generated is different each time, right? It may be that due to just uh, the nature of how the business logic works, or something about the implementation. It may be that they're getting different values um, of the random number generation on replays, or when you want to have progressible work is actually fine. That's typically not the case, but it's not impossible. So that's something that's worth keeping in mind, that how you define determinism can be relative to whatever your use case is, right? I don't. Generally speaking, IO in general is considered non-deterministic, right? Whenever you have to call out to the file system, or um, uh, make calls to the network, um, uh, generate random values, that kind of stuff. In some cases, even just offloading computation to different threads. I mean, it's computation, but also it's I/O, right? Because you're doing something off your current thread of execution. So, sending a piece of work to some thread pool should also be by default considered I/O, right? Yeah, okay. The question then comes down to preferences and constraints. What's your coding style preference? What's your coupling tolerance? What infrastructure dependencies can you tolerate? Stream processors like Flink and Kafka Streams use a continuous data flow programming model, which I think, quick sidebar. Well, it's not even a sidebar, it's just an observation. I do think that data flow programming is what was I gonna say? I think it's gonna become prevalent, or it should be more prevalent. Just because of how I think it leans more into the fact that pretty much any program, if you squint, you don't even have to squint that hard at it, right? It's a state machine. Even though typically people write procedural code, object-oriented code or whatever, at the end of the day, what your program is doing, your process is, it's data somewhere in memory, or in disk or over the wire, that gets loaded into memory, and then you process it. And that whole thing, it's a state machine. It may not be explicit as you're writing the code, or because you're just kind of writing things procedurally for the most part, but underneath it all, you are manipulating the bytes, in memory. And I think the data flow programming model is more amenable. Like, it makes it a little bit more obvious that there is a notion of state, and you have streams of basically data / bytes that you are just kind of processing. Like, it's like in that sense, I feel like that's why game engines are so interesting, or compilers, or databases, where I think it's less, that notion is less hidden from the from the developer or engineer, right? Because you really think in terms of, okay, you have different stages, you have your inputs coming in and different computation nodes that you have to travel, and it's like in the very first part of this series when he declares, rightly so, that it's all graphs, right? It's all it's all graphs, all the things, which I like to rephrase. My motto is it's all state machines. It's kind of the same thing. Yeah. So I think we were here. Okay. So with durability and batteries included, you likely already have a dependence on an event streaming system like Kafka. Flink is an additional runtime to manage, while Kafka Streams is just a library, but still comes with some operational challenges related to state management. Yep, state. So state is it's all state machine, man. All the things everywhere. Imperative microservices and functions offer familiar procedural. Yep, what I was just mentioning. Offer familiar procedural programming, but typically lack native durability mechanisms. To achieve reliable progress, you can couple reliable triggers like event from queues and all topics with manual progressibility patterns like idempotency and spreading logic across response handlers. Excuse me. Or add a durable runtime in the form of a durable execution engine for automatic state persistence and reasonability. Again, just encapsulating or wrapping your code in a bubble where it handles all the non-determinism. Okay, start with the mental framework. Building reliable distributed systems require thoughtful choices about coordination and progress. Architecture decisions are often about managing complexity in systems that span teams, services, and failure domains. We can simplify the decision-making process with a mental framework based on graph of nodes, edges, and workflows. The reliability of distributed work in this graph comes from coordinated, reliable progress of reliable triggers, progressible work, choreography, and orchestration. To summarize our model, the graph is composed of nodes, microservice functions, function as a service functions like AWS Lambda or Cloudflare's workers, Azure functions. Is that Google functions or do they just have Cloud Run? I think there is such a thing as Google functions. Yeah. Anyway, stream processing jobs and AI agents. Edges are RPC, queues, event streams. These vary widely in semantics. Some are ephemeral, others durable, which affects reliability. There are direct and indirect edges. Workflows are subgraphs. Are connected components, as in graph theory of the graph. Coordination strategies shape how workflows are built and maintained. Choreography, reactive, event-driven, provides high decoupling and flexibility. Orchestration, which is centralized or procedural, offers greater clarity and observability. Reliable progress hinges on two concepts. Durable triggers. Work must be initiated in a way that survives failure. Kafka queues and reliable RPC. Yeah. Progressible work. Once started, work must be able to make progress on adverse conditions via replayability, using patterns such as idempotency, atomicity, or the ability to resume from save state. Coupling is an ever-present property that must be balanced with other needs and constraints. Apply the model via your own decision framework. Using this graph model, we can apply a loose decision framework. Ask whether an edge should be a reliable trigger, and if so, what form serves your reliability and coupling requirements? Is it a direct or indirect edge? Ask whether a node needs progressible work capabilities and whether idempotency, transactions, or durable state persistent benefits your context. Yeah, actually, that's a really good question to ask, because you may not necessarily need all the overhead, and it's like if it fails, it fails. You just, depending on the kind of edge, right, the kind of reliable trigger that you already have that's pushing the data to the node, you may just decide, if something happens while the node is running the computation, then so be it, and you just don't need the overhead of making it resumable. Yeah. So, what programming style are you comfortable with? What infrastructure dependencies are you willing to take on? Consider the coordination trade-offs. Does this workflow need choreography's flexibility or orchestration's clarity? Is there a core workflow in here with only direct edges that can be spun out? Is the graph highly connected or dynamic? Consider the programming model. Do you prefer procedural code, or does a more continuous data flow programming model suit you or the problem being solved? Also, consider the complexity of the code written by developers and also the total complexity of the system. Durable execution can make some code simpler to write, but it's also another middleware to support, with failure modes of its own, just like distributed queue or event stream. Your specific needs will be specific, complex, with a number of constraints, but you can use this mental framework to define your own more rigorous decision framework to make more informed and balanced architectural decisions. I hope this graph model has been useful for you, no matter your preferences regarding the coordination, communication, and programming styles. A theme I had not expected when I started out writing this analysis was the unifying thread of durability. Durability is behind the idea that distributed work should not vanish or halt when something fails, whether in communication, in execution, or in system design. Durability underpins coordination and recoverability. Durability isn't just about data, but about progress too. It's a foundational property that can be built into functions, microservices, and stream processes alike. The only question is, in what form? And we are done. That's actually really short, considering the length of the other three. Kind of makes sense. It's just that it's the conclusion. I don't think he introduces any new concepts or whatever. The hard work was already done in the first three, and this was just a wrap up. I don't think there's much more to add than what we've already commented on in the last 3 videos. So short and sweet, I suppose. But yeah, takeaway is watch out, just like he lays it out here. Ask yourself a bunch of questions. Especially considering the trade-offs of the coordination you're going with, choreography versus orchestration. Also, it doesn't have to be one or the other entirely. There are ways to mix and match. Yeah. Well, this one ended sooner than I expected. I didn't glance at the article sooner, so I didn't know that it was going to be such a short one. I guess now we need to find something else to look at. Probably not this, because I'm pretty sure this is like a whole thing. Super long. Dairy fall. Well, the first entries, so where we can let's see, is there a way to okay, there's no clear way to just find out one of the first three, I guess. Frisbee spec. Been aware of Frisbee for some time now. Never tried it though. Frisbee.io. Can exhaustive test cases, injects faults, detects with any detects with conditions. Our tutorial. Should we do this now? It's either that or I have to clean up a bunch of tabs that I have open, which have so many, by the way. Let's see what I even have. The synchrony budget. Maybe another time. What if we could rebuild Kafka from scratch? How did I end up with this open, by the way? I don't know. I'm just gonna land it here, I guess. This is PLDI. Oh, this is the stuff that we looked at the other day. I mean, yesterday. Cafe Deck. Well, that sounds hardcore. Okay. Bilingual. X-ray. We believe a technology similar to X-ray, producing accurate internal knowledge fast and non-intrusively, is fundamental in taming the complexity of understanding software. Clear Blue is a tool. I guess there is a dot that's missing here. Is a tool that understands software in its opaque form, exploits efficient algorithms in decomposing and storing its behavior as data, provides extension power to enable versatile downstream applications. This talk covers the challenges of Clearblue, sets to tackle the outline of how Clearblue works, and say, oh, this could be really interesting. I'm actually really curious. Oh, here it is.
Last keynote speaker is Charles Jiang from
I guess we found something to dig into.
University of Science and Technology. He will going to talk about his journey to build a static analyzer for enterprise scale software. Please give him a big hand.
Thank you.
Is this open source anywhere?
I'm from Hong Kong University of Science and Technology. Been working in static analysis for many years. So this is a talk about almost more than 10 years of experience in doing this research. Of course, joint work with all my previous and current PhD students, around 12. So many of them have already graduated and made more money than myself. So outline today is I want to give an overview. So my talk today is very high level. I promise that there are no inference formulas. There's no inference rules. There are no induction formulas.
It's not available.
I'll be mostly talking about the umbrella project that includes many interesting ideas. I want to focus, after the introduction, I'm going to focus on a few key ideas relevant to static analysis, mostly how to do path-sensitive data flow analysis. And then I'll talk about a few future directions of this project. Okay? So this project name is called Clearblue. So it happens later I found out there's another product that has the same name. That if you smile, that means you're still very young and healthy. Okay, no smiles, good. So this is it's a keynote speech, so I have to do something proactive. So I'd like to open with how to save static analysis. So maybe arguably that's my personal view, but I feel that static analysis is somewhat on the decline in the past few years. Last year we published a paper is about buffer overflow detection, just to give you some ideas why I feel that way. Right? So last year we published we won the paper work, significant work on buffer overflow detection. Right? So buffer overflow, this is where the static bug finding started. We found out that where the earlier paper was published 14 years ago. So that's how few people have worked on this in this area. And static analysis was never sort of a mainstream technology. Right? It was never on the center stage. It's always sort of good to have sort of technology. But is there something wrong with this area, with this field? The answer is, of course, no. So let's look at another piece of static analysis technology, which is called X-ray. Right? If you think about it, X-ray is doing static analysis for real-world objects. Here's the inventor. Almost immediately, he invented X-ray at the age of 50, or around my age. He immediately started to get medals from the king, and then he's actually the first Nobel Prize physics winner. All right. So that's how successful static analysis in real life is. Actually, it's very fundamental to many mainstream applications. Right. So it's a successful static analysis piece of static analysis technology. So I keep wondering that how we can learn from that. Right. So the two things that attract me the most is that first, X-ray is very easy to use. In addition for giving a good image of what's inside of you or the objects, it is very easy to use without any intrusive preparation. Right? And also that the output of this technology is just data, is image. So it doesn't really make any assumption of what your intention is. So would like to, software, of course, nowadays is, I think it is as important as any physical objects, real-world objects. I would also love to have something like X-ray for software. Right? And I claim that we don't have it yet. We don't have it. So the input is a software, is software by itself. It's not source code, it's software. It's the software that people use. The output should be the data that describe what the software does. And I claim that doesn't exist yet. So does that really mean that for researchers in static analysis, are we really not that smart? Or are we really not working hard enough? The answer is, of course, I can only say for myself.
Yes.
I'm working enough, very hard. I think I'm smart. But I think the reason is because the static analysis is really, really challenging. Okay? This is meant to summarize for people who really have no idea what static analysis is about, but we analyze programs, right? So for this very simple piece of program where we try to analyze, we focus on the variables, right? These represent the data in the computation. So you look at it very quickly. There are 4 variables in the program. But if you really programming, you think you understand programs, you know that some of the variables actually takes inputs from other variables as part of function argument passing. So that actually produce more possibilities for the values. But if we consider where the function is called, the function can be called multiple times. This is what we refer to as context sensitive. We actually have to double the size of the variables that we need to look at. Okay? So it depends on where the location is. The variables take different values. Then we take paths into consideration. Right? Paths means all these if-else branches. If we take those into consideration, we double the number of variables. Okay? So relating to X-ray, this sort of describes the granularity of the image. Right? So of course, the higher granularity that we're able to look at, the better quality of the image we can produce for the behavior of the software. So the important takeaway message here is that we work so hard on the algorithm. Right? We try to speed it up. Right? So we have a cubic for pointer analysis, for example. We have subcubic improvements on the analysis. But don't forget that the base n is already exponential. Right? So it doesn't matter how fast your algorithm is. The number of variables to consider is exponential. That's just a physical fact to me. So look at this piece of software. This is a Linux kernel, and we're able to really accurately compute its call graph. Right? So this is a call graph of 381,000 functions. Right? So if you take this into your picture, combined with this story, it's not because we are not smart enough or not working hard enough. It's because this is a real monster. Right? It's just so hard to be able to. This is so complicated than any of the physical objects. Right? So that's why X-ray can succeed. We haven't found it yet for software because it is just so complicated. And there are even more bad news. I work with enterprise a lot. So enterprise means that these are the big software that provide sophisticated ongoing services for many people, okay? Such as the Linux kernel. So they're not only big, they're also changing, they're also alive. From Linux kernel, every 6 minutes there's a commit. Okay? So this is very easy to tally. You can look at the GitHub data. Of course, as how we develop software is getting more mature, any mature manufacturing actually has more integration than development, right? So you actually purchase software from other vendors. You take open source software and then you put them together. Right? So this degree of integration is only going to get bigger and bigger. Right? So which means that in your software, the software people really going to experience. It's going to have a lot of what I call dark code. Means that the software you have no control of. You don't even know what's inside. Right? You purchase them through its compiled form. And also this push of what we call cloud native means that we write these lambdas, right? Lambda programming. We partition our programs into microservices. Right? So this is how we built for these big scale software. So easy to develop and very elastic. Right? So which means that the program that you write as a developer is very small, right? So when you apply your static analyzer, it's going to be very happy. It's going to chew your software for breakfast. But it has nothing to do with the end quality of the whole system, because the whole system is very big and complex. So how to do static analysis in that setting? Of course, also the knowledge we extract from software.
I guess I could just look at the videos instead of going through.
And often companies that I work with often require us to solve all of these problems. Otherwise, what's the point of using your tool?
They have a playlist.
So that's really the scary story.
Anyway.
So from these observations, here's something that we want to build. I think that sort of behave more like an X-ray for real-world objects. Of course, the basic premise is that we need to produce somewhat good-quality image. Also, we want to actually produce the image through a non-intrusive imaging. Right? So we don't want to actually interfere with software development cycle too much. Ideally, we like to scan software from their product form, meaning mostly compiled code by code. And just because of the sheer size of enterprise software, we have no choice. We have to learn from how people deal with big data. We have to use distributed computing cloud infrastructure to analyze it, and we have to do incremental analysis. Otherwise, it's impossible to handle this.
Yeah.
And also,
my guess is that Yeah, actually, I don't know. I know that there is something called abstract and interpretation. Something. I think I recently came across a tool called OE. It's from the folks at Okamo. Well, I don't know if it's the actual Okamo. It's a French company with strong Australian programming. Yeah, okay. These guys, whoever they are, French. Yes, they came out with OE. Sorry, I got distracted by and I haven't. I mean, I became aware of OE, but I don't think I've ever visited this specific page where they list out stuff that they've done. What is the M language? German has a lot of weird syntax. Is this just an IR for other languages to target? Yeah, I'm not sure. This is not giving me much to work with here. Okay, well. Yeah, OE. So it's it basically helps with running C, C++, Rust, and Zig. I feel like they just added Zig. I feel like it was just C and C++ and Rust. I don't recall seeing Zig on the list before. But this is actually pretty cool. Like, you can test your Rust or C or C++ code using this. It's basically like a test harness that does concolic execution, I believe it's called. Let me see. There are some examples that symbolic execution. Could have sworn that. This can be the case with factor optimizing the function. I think there are any more example of bug finding. Gosh, now I need to work on the documentation there. Which there are a set of good examples. Can't find them right now. Oh yeah, abstract. Yeah, fuzzing and abstract interpretation. Okay, yeah. So yeah. So you have your program. You write it. Then I don't want no value. That means, but anyway, you basically run it using, I guess, the binary, the OE binary, and it will basically flag stuff for you without you having to, generate test cases or anything like that. It just handles that for you. It's pretty neat. We need more tools like that. Yeah, so in terms of taking the X-ray, I'm guessing it has something to do with um, you have to start at a pretty low level to make it even like tractable, right? Like, because first of all, you definitely don't want to have an X-ray that is specific to a given language. Um, you want something that aligns with the philosophy of language servers, where you have a common protocol, and you can have different implementations for different languages, but they all use the same protocol. You will also want to leverage stuff like the LLMVM IR, where you have multiple languages that use that as a backend. So yeah, something to do with taking some sort of generalized IR. Yeah, I don't know. I don't know if I have anything more that's interesting to add to that. You probably want some program slicing capabilities, meaning that and it's something that actually crosses my mind often, which is it would be great if for every single like dependency package or lib that you have, that you are able to just have a simulator that's completely uh, I guess um, gosh, that act as a program slicer of some kind. Basically, you are able to figure out all the features that rely on that particular module. You're able to generate some sort of top-down dependency, or I guess topological sorting, and you are able to collapse all the incoming dependencies into a single runtime dependency that you can mark via the simulator. And you don't have to worry about the downstream dependencies, because you are testing the module in isolation, so the children dependencies don't matter. It's mostly the parents that you want to you want to consider in your simulator engine. And what else? What was the other thing that? Also, yeah, having really good tooling to separate the memory/data semantics from the behavioral semantics of a particular module. And understanding, like basically being able to understand the flow of data within the module itself, and how that can be affected by the the state space of its inputs. Yeah, I mean I'm sure this is just a bunch of words, but I'm sure that whatever this X-ray is touches on a bunch of these ideas. But fundamentally, right, your program is a state machine, which means state/data/memory. Like, you have to, whatever this is, I don't think you can have a tool like this until you have a truly, well, like you have you have a way to truly express or lift or unravel, is that the right word, or reveal the memory slash data semantics of the program. Now, to which level you do that, I don't know. Do you have to do it all the way down to the register level? I don't know. Yeah, anyway, let's keep going.
The goal of the static analysis is to produce data, is to produce general forms of data, and we're going to let APIs, DSLs, LLMs to look at it in any way they like. Okay, so this is something that me and my group we've been trying to build for the past, let's say, 7-8 years. So the answer to that is
Did you do it?
the Blue project. So here is the architecture of the tool. It's two-chain. So what intake to the two-chain is basically binary. Okay, so any forms of binary or Java bytecode or the machine binary.
LLVM.io is involved, right? Because you definitely want to be as low. As close to the machine code. In the process of generating the machine code, you want to be as close to that as possible, so that there's actually less work for you in terms of producing truly correct specs slash semantics of the programs you're trying to verify or you're trying to x-ray in this case. Yeah.
So our tool is
like another example would be if you're given the choice of making either how do I put this? Let's say you have a set of Rust libraries, Rust crates, and you're told that your job is to make sure that all of them are formally verified to be correct for a given set of specifications. And let's say that there are, 8 of them. You probably are going to have a better chance of succeeding if you're able to, first of all, understand the class of, given the spec of all 8, find a way to, build some sort of compiler tool that will basically be reusable across all 8, rather than trying to verify each one in isolation, basically.
We're not doing decompilation, we're doing lifting. So we're lifting these binaries into, we choose to use LLM-IR. So we're lifting them into IR. And then on top of that, we do a lot of interesting static analysis, such as call graph building, pointer analysis, a lot of type inference because we're lifting from binaries, so there's a precision loss. So after that, we'll produce some kind of graph representation of the behavior. Basically, it's a PDG. Okay? It's a program dependency graph. On top of that, we have a lot of techniques of finding specific bugs. Okay? So these are the papers we published describing different parts of this two-chain. So if you're interested, you can find more details. So this is just what I just described. So what we try to do is we basically try to build whole program PDG. It's not an easy task. And then we store it to disk. We build indices so that we can look up fast. And then we support analysis on demand. So these are the different, I just basically just, I have more details later, but these are just the different basic steps of how ClickBlue works. Okay? So the main technical features of ClickBlue is that we basically are good at or focused on doing value flow analysis. Okay, so not we don't have, for example, a lot of value abstractions or handling things like abstract interpretation. We don't focus on that kind of problem. We focus on value flow problems. We're pretty precise, not as of course as ideal as we wish, but we can analyze an external, for example, 30 million lines of code with 6 layers inlining and full path sensitivity. Okay.
That's a lot of code.
Asynchronous analysis means that we are pre-processing these programs and we extract some representation and we store them onto disk. And then we query later. So when you try to find, for example, bugs, you can write queries and extract this data from disk. is non-intrusive analysis, right? We don't require you to modify any of these your manufacturing process, right? So one painful lesson for any static analysis person is that when you try to deploy it in reality, you're going to face with what I call the last mile problem, is that you have to modify how do you extract the symbols, right? So you have to modify the product development cycle of the software company, and which is the last thing they want to do. Okay? So by analyzing binaries directly, we can do it out of the box, so we can support all of the major binary formats, including Java bytecodes. So we have some APIs to facilitate very quick definition of value field queries. Basically, they are just graph traversals. Okay. As a joke, I think you probably hear the joke already, is that everything the PR community is doing is trying to repeat what database people already did. Okay. So well, in our case, it's sort of the same case, right? So this behaves indeed like a database system.
Yeah.
So next, I can let's try to be a little bit more technical. So let me talk about some of the essential innovations that we did for inside the loop. So again, this is like almost 10 years ago. So originally, we published a paper PLDI 18 called Pinpoint. So basically summarized the core techniques that we still use today. Okay. So the main idea is that for enterprise scale software, so some people are going to probably hate me for saying that, but we give up on soundness. So for software of that size, soundness is not that useful because it gives you too much information. Right? So for developers, it was just impossible for us to filter out anything that's really valuable. And for software of that size, precision is impossible to achieve. And so how do you know the report of the static analysis result is precise? Unless you give it a POC, right? Unless you give it input and produce the plot. Well, how can you analyze all the way to the main function? Sometimes you don't even know where the main function is. Right? So precision is impossible to achieve in this way.
Sometimes you don't even know where the main function is.
Something.
Oof.
Something. That's
true words
have some value, right?
have not been spoken. Yeah, it can be that bad.
So which means that we want to have the highest,
especially when with enterprise software and how prominent using frameworks and wrappers and layers of abstractions. It's yeah.
Possibility of precision, which is path sensitivity, of course, plus context flow, all these sensitivity fields. Right? So all these sensitivities we want to, in particular, bring path sensitivity into the picture, but with a fixed window. Right? So with fixed levels of context. So hopefully we can produce some good results in software of that size. And the core idea is not really, I would think that we actually borrowed a lot of good ideas from existing work. So our focus is to try to address path sensitivity, so borrow from a famous work Listo, that we encode a path condition as a Boolean variable directly inside the PDG. So using path condition as a variable, later I'll have some examples. Use path conditions as variables allow us to actually pre-filter a lot of obvious contradictions without really calling set. Right? So set is another monster. We do perform point analysis, but we're going to do it purely local. Right? So intra-procedure point analysis. And then we borrow ideas from Saturn to explicitly expose the side effect across the function boundaries. Okay? So why do we do that? The end result is that those people who are familiar with conventional value flow analysis, that you can imagine RDS, supergraph, but with pointers all resolved, and with path conditions encoded inside. All right? So that we can do one traversal of reachability query, and then we can collect everything into one query. Right? We don't have to do a separate path-sensitive point analysis. We can do everything in one traversal, in one query. Of course, there's the ugly side of it. That's at the bottom of the slide. That's why it's very ugly. Is that we have to impose very harsh limits on how we do that. Right? So, for example, our inline levels. So the context level we can look at is capped at a number. So usually capped at 6. And since every load store pairs are created with path conditions, we have to limit the number of different paths that each load store pair could be matched within a number, typically 10. So this is the sort of the limitation we impose so that the analysis can actually finish. So just give you some detailed example of what I just said. Right? So given the program on the left, we have some pointer operations where there's a load and there's a store. Okay? So our first step is to transform this program into another program that will directly expose the side effect of input and output. So the input is a pointer P that's being loaded, which means its content is being accessed. So we actually produce what we call auxiliary variable on the input, which is integer x. Since P, the pointer P, is also being stored, which means that we have to produce another variable. So the function, the test doesn't return any value. In this case, it actually returns a value, and we actually explicitly change this function to return the value, represent the side effect that are coming from the pointer. So in transforming that, then we transform the caller, which is the main function, so that the result is that everything is purely data flow. Right? We don't have a two-level pointer here. If we have a two-level pointer, there will be a sort of the alias that also flows. But after this transformation on the graph on the right side, there are no pointers.
Well, data flows.
If the data is actual literal integer or float, you will represent the flow after that. If the data is the address, it will represent the flow of pointer. So given this graph, we can do on-demand analysis. Right? So when query, if the malloc can flow into the man copy in main, we can just identify the source and sink and try to compute path-sensitive reachability. Right? So another feature is that since we represent this path condition using a Boolean variable, we can just use the Boolean variable to represent the path condition. So in a complex graph, there will be interesting results when we abstract actual path conditions, just use Boolean variables. But this is basically what the core idea is. So with this graph, you can do CFR reachability if you do top-down, or you can do cloning if you do bottom-up. Right? So it's up to you to how to do your search efficiently. But it's purely on demand. There's no pointer to solve. So this is great. So we can do pointer flow and data flow in one shot. There's no separate stage for doing pointer analysis. So this actually saves a lot of computation. But we hit another bottleneck is because we try to do path sensitivity. So as you can see, every query involves set. Right? So set is basically becoming a big bottleneck for performance. In this case, we identify that set formulas actually takes up a lot of space. So the process of finding bug for pinpoint was bottom up. So we compute summaries and we actually inline bottom up. But doing that, we found that a lot of path conditions has to be inlined, has to be concatenated. And this actually hurts scalability a lot. So the observation we made in this paper is that we can actually only store path insensitive information, sort of doing a path insensitive inlining. And once we found an interesting path in the value flow for bug finding, we can actually recover all the path conditions from the IR itself. Right? So we just look at the 11 IR, and then we can just retrieve all these path information. When we look back, it sounds very trivial, but somehow people know it's, at year 21, people recognize it's a good idea. Another observation we make is that once we know the program structure, we can actually save a lot of effort in coding path conditions. For example, in coding path condition for function foo, we have to consider how these variables flow inside function bar and come out. Right? So usually we will encode everything with a big formula. A quick look into the function bar is that we found that the input and output has no other path conditions. It's just a linear relationship. Right? There's no use to encode all these linear relationships. So it's equivalent, just ignore whatever's inside, and then encode the condition directly. It would be, so in terms of set, it's the same result. Right? It doesn't really affect anything. So by leveraging the program structure, we can actually speed up set a lot. So this is what we did follow-up work in PLDI 21. The result is, of course, the big saving is on memory reduction, so we save a lot in storing these path conditions. The memory reduction is quite considerable. There's also follow-up work on that, which is ongoing, so this is unpublished, but I'm happy to talk about it. Is that the earlier work we saved space, now we try to save time. Right? So how do we save time? Is that in old IPS problem solving, basically there are two approaches, right? So one is the CFL reachability, where you from top to down, and then the downside is that every time your query changes, your summary has to be recomputed. Right? So although you only traverse part of the graph that's relevant. The flow-based solution is interesting. It saves a lot of.
That's what I was asking earlier. Wouldn't top-down have the advantage that you can focus on a particular program slice or slice of the program? Because now you can, I don't know, query for a particular region of the program with the top-down approach, and you don't have to basically load or process whatever nodes or edges are irrelevant to the search/query of the slice.
Effort in reusing some of the clones. And if you have multiple source and sink, you can probably also address that as well, because you're doing inlining, you are actually probably looking at, on the way, you can do more discoveries of other source and sinks. But it requires a lot more memory, right, compared to the top-down approach.
I would imagine so.
So we like to combine both. So we like to do reachability. We like to only traverse.
I would say this is some serious research, and I'm just sitting here on my chair making these comments. But yeah, intuitively, I think, given the context, which is wanting to X-ray programs, I think a top-down approach just seems to be, all things considered, probably the more I hesitate to use this word because I haven't done any research in this whatsoever, but my hunch is that it's more optimal to go with a top-down approach.
Part of the space that's relevant, but we don't want to actually clone the summaries. Well, we do clone the summaries, but let's do it in a different way, right? So the difference is we can clone the summaries, and we store them on the disk. Okay? But we don't just naively clone these summaries. We pre-compute reachability. Right? So using CFO grammar and set. So we pre-process these summaries. It's just for value flow purposes. Okay? And we store them on the disk. The perceived performance is that when the users are actually using the tool, the perceived performance can be greatly speed up by loading these summaries from the disk instead of actually computing them. Right? So we can only look at the sort of additional lag when we know where the source and sinks are. We just look at the additional lag in their intra-procedural inside their function, and then the rest of the paths can be actually looked up by from a table, right? What table? This table. So this is a quick example. So these different colors represent the entry point and the exit points of these function summaries that we built. So the summaries are similar to the ones that I just talked about before. Then from that, we compute sort of the value flow paths. Right? So for example, there's an entry point to a function. Let's compute all possible paths that can come back. Okay? Of course, possible means that they have to boundary problems. So what are boundary problems? Boundary problems are the parts of the software that's missing. So there are many different scenarios why they're missing. Of course, they're missing. Right? So that's one scenario. The second one is that they're in binary. So recovering from binary is a challenge by itself. Some binaries are heavily obfuscated. Okay? I have also seen other applications that the binaries are dynamically downloaded, so it's just impossible to have. But then there are also limits of static analysis, as well known. For example, understanding of shapes in a big scale, right? In a big scale. Plus loops, right? I.e. Recursion. So these things are very hard to analyze, and also because of the size, right? So it's just impossible to be precise. So these are things that are impossible for static analysis to address, but the users, they don't care, right? So for them, this is their software. They don't care how you do it, but please give me some useful results. Containers, collections, abstract data structures. So these are things that are very hard for static analysis to get accurate. For example, we can store something into a hash map using a key, and then we can use the same key to retrieve it, right? When we do that, we know that these two results are the same. And then with that, we can establish a data flow, and then we can proceed. Analyze a lot of interesting plots. Otherwise, it's broken, right? Modern software uses this a lot, so a lot of the paths are broken, which is not good. But it's not so hard to analyze for human. So our intuition is that for certain kind of API pairs that come with the containers, as a human, we can actually quite easy to deduce that certain things are aliases. Right? So for example, push and pop. Right? So when you push something, then you pop, you know that very likely, right? When you push something, you pop immediately. That's a trivial case, but you know that these two things are obvious aliases. Otherwise, it would be very difficult for static analysis to give you that conclusion. It's very easy for human to deduce that. So what we do, we first look at the type signatures. We read the documentation. Right? We read the documentation. We read the type signatures, and we read the document. We actually read the sentences, and it's not hard for a human software developer to reach.
I guess you can leverage
so this is the intuition we had.
Case,
right? Observations. Just quickly skip them. So if we combine them, we ask LLM, and we combine with these type constraints. We combine them together. So let's see we can make some right conclusions. So this is called so this project is called Infer. It's in the last year FSC. So the result is that it's quite interesting. Right? So these are the things that static analysis, which no oracle to compare to other than from a sort of subjective judgment. Right? The precision that we call are reasonably good, right? So around 80%. And most importantly, we can find additional flows, right? Compared to a thread does not really acquire logs in successive manner. Okay. This is that it actually passed into these structs. Okay, so this is some very easy. By 800 kernel functions, 200 wrappers, 200 free wrappers, and 400 non-memory management wrappers. So this is a benchmark, not from us. So we're going to use it to test, to compare the capability of ClearBlue versus LM. Okay, so this is the experiment. So we implemented an algorithm for dedicating to find memory wrappers on ClearBlue, and we compare that to LLM. So we see who is doing better. Some details about how we do it. So we picked some of the newer models as well. Some details about the prompts that we use. The result is very interesting. So we first prepared the benchmark about 20,000 candidates. So these are the random candidates. But so there's no oracle for this kernel. Right? So but we try our best to filter out 20,000 wrappers. And inside the 20,000, we're going to see how many of the wrappers, true wrappers, can be picked out, because we have some oracles, some known facts. So that's the way that we compare. So this is how each model, how many wrappers that each model picked up. Okay? So for example, out of these are there's a sort of man-made benchmark. Each model can pick up a small subset of these wrappers. In terms of quality, we just look at how many. So among the wrappers that pick up, how many of them are in the oracles that we know they're accurate. In this oracle, there's 800 calls. Okay, so that's what we do. So the observation we make here is, surprisingly, LLM model in this task outperforms ClearBlue by a very large margin. Okay, so this is what we. In terms of recall, they are roughly equal. Okay, so this is for the this is for the allocation wrappers. This is for the free wrappers. This is for the free wrappers. So the LLM models are also on par with the static analysis. So in this way, actually everything is roughly equally good. Okay. So here are some case studies why for some false positives and negatives for this comparison, right? So this is a case where agents where in analysis is still a very big challenge. I think not because it's not important, but maybe we have to try to look at.
Okay, so they're planning on open sourcing it.
There's a need to bring static analysis to product process.
Please do.
And we'll continue with data-driven static analysis. And I think static analysis is also good on high-level abstractions of when you produce doing static analysis on network protocol interactions. This is having great success in that you can don't have the scale problem. And we're also experimenting with agentic approaches to work with LM to actually produce POCs for the bugs that we find. Okay, so I think that's more valuable output for the users. I think that's it. Thank you so much. I have a semi-working website that tells more information, but don't trust too much on that.
We have a couple of minutes for questions. Any question?
Thank you for your good, very good presentation. I have a question about the memory identification and how it can be used in scenarios. How can memory identification be used?
The wrappers are they act like a disguise of something very important. They look like regular functions, but they're actually very important compared to other functions. So memory wrappers are memory allocators, for example. The variables returned from that is probably worth attention. You might want to sanitize it, or you want to actually, do buffer overflow checks on these targets. And so otherwise, you're going to do buffer overflow on any of these variables. But if you know that it comes from a wrapper, then you probably can focus your analysis on that. And also things, right? So frees. If some memory is free, then you probably need to look for double free or use after free problems.
Also, in the sense that we may focus more on such.
Yeah. We want to know that certain variables represent important information.
Thank you. Thank you very much.
Any other questions? So let me ask one question.
So this is maybe a super specific question, but you had this example about trying to detect the deadlocks with the interrupts.
Yeah.
So I was wondering what actually the problem was in the example that you showed, because it seemed that there would only be a deadlock if the interrupt in turn was interrupted again.
Yeah, there will be another thread. I didn't show the big picture, but there will be another thread and another interrupt. So they will be forming. So you log 01 and log 02, the other one log 02 and the interrupt log 01. So when the interrupt comes, that the thread has a lower priority, right? So the thread will be suspended. Right?
Well,
so
you need two interrupts to interrupt each other for the thing to be a problem or not? Because your handler did the unlock. Your interrupt handler, and I guess.
They have another interrupt. Okay. That could actually form the So the problem is look at the program flow. There are no nested locking. When we consider interrupt, there will be nested locking. So that's that's it.
Actually, let me just do this. Ba-ba-da-ba. "96 videos? Oh my." Let's see if there was a quick lecture. It's not as long as the first one. Scalable value code translation for entire projects. Oh. Might come back to that. Oh, that's too long. Consensus protocols. Should be interesting. a prophecy-based refinement type system for Rust. Definitely want to see that. I mean, yeah, at least it'll say that. Spatial data flow. Oh, well, automatically fixing data races at industry scale. That's some big brain stuff right there. That's money. That's with tensor computation. First classification dialects for MLI. Oh, that could be really good. MLIO is everywhere now. Well, it's growing. So much good stuff. You know, I think I'm just gonna pointer analysis for database-backed applications. Symbolic reasoning for SQL using conflict-driven under operation. So much good stuff to look at. Okay, let's roll back up. I think it was something to do with Rust. Well, it was. Yeah, it was, no, wait. There was one relating to Rust, but I don't even know if that was the one that I really, that my interest really got, was grabbed by. Okay, yeah. Yeah, but that's not the one actually. I think it was, yeah, I think these two actually. Interested in checking that out right now. No, not that. Where is that? Yeah, this one. Wait. Oh my gosh. I have another window. It's not as if I already have so many windows with so many tabs. Here's another one. Another one.
Okay, great. So for our next talk by Hanlang Zhang and collaborators about scalable, validated code translation of entire projects using large language models. So please, get started.
Hello everyone, I'm Han Zhang, a PhD student from the University of Bristol. I'm very glad to present here our work, Scalable Validated Code Generation of entire projects using LLMs. This is a joint work with AWS, and my collaborators are Christina and Mon from Bristol, Brendan and Daniel from AWS. The background of this research stems from the industrial need of translating security-critical code bases into Rust. Specifically at AWS, we encounter practical need to migrate several code bases. While there exist works that rely on symbolic techniques for automatic code translation, the code produced by such tool is often not idiomatic, and thus less maintainable. As a result, we proposed to develop an LM-based tool for translating existing Go source code into Rust. However, real-world code bases are often of large code size and are organized into complex file hierarchy. While LMs have shown their power of producing good quality of code, the limitation of context window blocks us from translating whole repositories all at once. To scale up, the general approach we follow in this work is to modularize the translation query. A repository is partitioned into individual translation units, like a function, a type, or a global variable. These code fragments are then translated by the LM following the dependency graph, producing code fragments in Rust, which are later on combined into an entire project. However, being modular is not sufficient in itself. When applying the modular translation algorithm, two key challenges arise. Firstly, we discover that LMs are often unreliable when translating features of the source language that do not have a direct mapping to the target language. For example, in this Go program, a global variable x is initialized by calling a function. Without specific instructions, the LM can produce Rust code that largely simulates the syntax of the Go program, where the static variable is initialized by directly calling the function as well. However, this is invalid in Rust as set of variable can only be initialized by custom expressions or custom functions. Therefore, this default translation do not compile. There are multiple ways to salvage this translation. For example, one can rely on the lazy construct from the standard library, which supports lazy initialization and therefore allow initialization by calling functions. Similarly, one could rely on third-party libraries that provide the same functionalities. And there are perhaps many other solutions. While the LM can sometimes generate correct code fragments, there is no guarantee that these fragments consistently use any of the solutions. To resolve issues like this, we propose a technique or feature mapping that incorporates predefined high-level translation rules with LLM's code generation. These rules specify how particular source language features should be mapped to construct in a target language, and allows for customization. This approach improves both the compilation success rate and the consistency of the generated code. Secondly, it is challenging to validate translation in terms of semantic equivalence. Since we translate the program modularly, we aim to measure semantic equivalence at the function level. Here we assume that the Go program comes with a suite of unit tests that achieve high functional coverage rate. While these unit tests can be used as specifications of the original functions, it is not obvious how we can transform these unit tests into functional specification of the translated Rust functions. It is especially challenging when the function signature involves non-primitive types or user-defined types, as LLMs may generate code that contains types that are not compatible with the original source code, meaning that the runtime values witnessed by executing the unit test cannot inhabit the Rust types. In this work, we propose a technique called type compatibility check, which dynamically checks that a Go type and the Rust type can safely interoperate, allowing differential testing of the translated Rust functions. We incorporate the two proposed techniques into the module translation workflow. Before starting the translation, we collect execution snapshots for every function in a source project. Execution snapshots are a pair of input-output examples that serve as specification of the functions translated. For each partition code fragment, we construct feature mapping prompt that specifically instruct the LM for target features, obtaining a candidate Rust code fragment. And this fragment is then statically checked against the corresponding feature mapping rule, and dynamically checked for type compatibility by using the execution snapshots. If any of the checks fail, we recreate for a new translation. We set a final budget on the number of regeneration to avoid infinite loop. We call this translation process a type-driven phase. After type-driven phase, we obtain a type-compatible product translation, and we apply an additional semantic-driven refinement phase. We run the oracle constructed for all functions. If any of the tests failed, we recreate for a new translation with signature frozen. Again, we set a budget to prevent infinite loops. After all functions are refined, we combine all the code fragments to an entire project as the translation of the original project. Now we go into details of our two techniques. The first technique, which we call feature mapping, comprises predefined high-level translation rules for prompting and checking LLM's code generation. For the code snippet containing global variable initialization, as discussed before, we apply this particular rule. Note that for clarity, we summarize our predefined translation rules by using a slightly non-standard inference style rule. We first check the shape of the source code, which is the global variable initialized by a function. Then we construct the prompt, just specifically instruct the LM to use the lazy construct. While doing so, there's no guarantee that the LM will actually generate the code we want, or even any code that makes any sense. We therefore apply static checks on the generated code to enforce the rule that the code is indeed a static variable initialized by the lazy construct. Note that we don't impose any additional constraints, and the LMs are even free to generate names of the global variables. This is for idiomaticity purposes, as Go for counter cases, where Rust prefers snake cases. Now, if the check failed, we give up the current translation and recreate for another one. Once obtained code fragment that satisfies the desired pattern, we perform post-processing, which is not necessary for this single case. So in summary, a feature mapping rule comprises three parts: a specific instruction in prompts, the static checks that enforce the rules, and necessary post-processing steps to instrument the code. Of course, there are many other differences in features between Go and Rust, like error handling mechanism, where Go uses error return value, and Rust uses result enumeration. Also, there are huge gaps in programming abstractions where Go uses structural interface and Rust apply nominal traits. These challenges can also be handled by our feature mapping rules. We have rules that map a followable Go function into a followable Rust function by requesting and checking the usage of result enumeration and a specific error type called anyhow error, which is a third-party dynamic error type, allowing passing between dynamic error. Similarly, common coding patterns in Go. Note that these kind of rules allow for customization. The user can choose different error types to map into and modify the rules and prompts accordingly. Also, we have rules for systematically and modularly map an interface and its implementations with Rust tray and implementations. Note that this rules requires post-processing of the code generated by the LM in order to preserve potential sub-interfacing relations. For detailed description of these rules, we refer to the paper. All these rules contribute to higher compilation success rate. Also, by applying these predefined translation rules, we have a very clear understanding of the code generated by the LM, which facilitates manipulation of such code. For example, combining code fragments without fragments, constructing oracles, etc. After obtaining candidate function translation, we need to consider constructing an equivalence checking oracle. We follow a differential testing approach. We first execute all existing unit tests for the Go project to be translated. For every function covered by the unit test, we collect execution snapshots, which are pairs of function input-output values. These input-output values are then ported into the Rust program by using serialization and deserialization, where we construct a test harness such that we execute the Rust function with input values from the execution snapshot, and check whether the Rust output equals to the output values from the execution snapshot. Note that these steps require that
do you already,
be compatible for interoperable.
Do they translate the test by hand, or do they also generate that? My guess is that they actually translate the test by hands, because I mean, there are the tests. You don't want to let the LLM do that for you. I mean, at least the Oracle, whatever. I don't know. I feel like that's what will make the most sense.
Additionally, we model side effects such as global states, input states mutations, which are omitted in the above diagram. In our experiments, we noticed that sometimes LLMs generate translations with incompatible type, which lead to incompatible function signatures, causing the equivalence checking oracle to crash. For example, consider this Go function that takes a slice of string as inputs. The LM can generate a plausible translation, which is a function that takes a vector of string as inputs. This translation is incorrect because upon checking execution snapshots, we found that the null value has ever been an input value to this function f. However, null value does not inhabit the Rust type vector string. Recall that we differentially test the Rust function by porting Go values into Rust. By deserialization, this process is doomed to crash at runtime. As a result, we devised the notion of type compatibility, which says that any feasible values that can inhabit type in the original Go project should also be able to inhabit the corresponding type in translated Rust project. Type compatibility ensures the equivalence checking oracle can construct it without runtime crashing, and can feature our run translation early. During the translation, we enforce type compatibility check. For the previous translation, we looked at the function signature and found that the input type is not compatible with the original input type, as it does not permit the null value. Thereby, it is rejected, and we proceed to requery for a new translation. Now, the input type of this new translation is wrapped by an optional, and therefore null value inhabit this type, and so does any other values. This time, the function signature is type compatible, and we accept it and proceed to later phases of the translation.
It seems like this is specifically from Go to Rust as opposed to a general purpose thing. I think if you wanted to build something that was general purpose, again, I think you have to go the IR route, where you somehow find a way to have the semantics of the source programs encoded in such a way that you can then retranslate or port into multiple languages at once, actually. And each language will just interpret the same semantics in its own way that's suitable. It's almost like you have like a universal semantics IO, the way that you have the OpenUSD spec, the open universal scene description. It's like a 3D scene graph description language. I think it came out of Pixar. You know, you need stuff like, I mean, you will need something like that conceptually in the abstract, where you can universally express the semantics, and then each language can then map its understanding of the semantics into its own. I think the one-to-one mappings are fine, I guess, but it just doesn't scale if the goal is to translate as many programs as possible and do it basically on demand without too much upfront work, right? And have the most of the stuff just be automated. Then I think we definitely gonna need some sort of I mean, to the best of my understanding, the closest thing we have to what I'm talking about is the LLM, not LLM, LLVM IO, I think. I could be wrong, but yeah.
To evaluate the features.
But I will say that still seems to be, well, that particular IO seems to be, it's probably too low level. I mean, I haven't done anything concrete with that involves processing that LLVM IO, but I imagine that for what I'm talking about, it needs to be a little bit more, or a little bit less lower level. Anyway.
To see of our approach, we select a real-world code bases as benchmarks, with size ranging from 300 lines to approximately 10,000 lines of code. We target at popular code bases, and we believe that popularity reflects the thematicity of the code base. Also, we select benchmarks that we view test of high functional coverage rate. Our experimental evaluation shows that our approach achieves very high compilation rate.
Oh, wow.
Measured by percentage of function translated that successfully compiled, we achieve an average of 98% of success rate. Our approach also shows a relatively high input-output equivalence rate. Similarly measured as the percentage of function translated that successfully passes our oracles, we achieve an average of 73% success rate. Also, the translation consists of 100% of safe code. We also ran an implementation study where we don't apply the feature mapping techniques, and the success rate drops drastically. Without feature mapping, LLM may produce code fragment that fails to compile, or fragment that is in conflict with other fragments, causing translation loop to halt quickly. We also ran an implementation study where type compatibility checking technique is removed. We noticed a drop in the success rate due to translation that have incompatible types. So as a conclusion, in this work, we developed a scalable code-to-ROS translator that can produce validated code. We propose two techniques, feature mapping and type compatibility, that improve the quality of the translations. And you can find out public artifact at this URL. And public GitHub repository is coming out soon as well. And that's so much for my talk. Thanks so much for listening, and any questions are welcome.
About how you're handling concurrency and transforming local to Rust code, both shared memory and message passing.
Thanks. That's a good question. We don't handle concurrency at this moment because that's a really hot feature. We believe that if there's a chance of defining like high-level translation with saying like specific concurrency primitives can translate into like corresponding ROS primitives or combination of ROS primitives, then we might be able to do translation. But for now, we don't consider concurrency.
Another question: how about how are you handling library calls?
That's a great question. So the benchmark we selected only relies on standard libraries or libraries of well-known third-party libraries. And typically, LLMs have the knowledge of selecting the corresponding library APIs, And we have an ongoing work that kind of extend the current framework to handle like arbitrary third-party library by using some writing techniques. So yeah.
Thank you.
Good. Another question over here, please, at the front.
Hi, I wonder how you check the equivalence of the two codes. Why the Rust code is considered as a correct translation of the original Go code.
Yeah, thanks for the question. As discussed in the previous slides, we kind of construct all codes by using existing unit tests from the Go repository. So basically what we do is that we execute all unit tests from the Go repository, and we collect execution snapshots, which are kind of like input examples for every function in the Go, for Go functions. And by using some interpretation techniques, we kind of ported this input example into Rust and use that as a specification for function translate.
Okay, we have time for a question. You have a question? Okay, yeah, let's have a question from you.
Thank you for the talk. How do you handle world checker? How frequently did it happen that the world checker rejected the translated program?
Okay, thanks for the question. So we don't particularly handle borrow checker. We kind of rely on the LLM to generate correct code. As you said, the borrow checker of Rust is very strict. It sometimes produce compilation errors, and we do encounter some hard cases where the original Go code is written in a really, I would say, not Rusty pattern, like you use share mutability, share ownership, and all that stuff, and such function cannot be translated. So yeah.
How frequently did it happen?
In our benchmark, it happens not so frequently. Like most of the code are translated just fine. So.
Okay, we have time for one more question. Maybe right here in the second row. And in the meantime, the second speaker can get ready.
Okay, so I want to argue that relying on the unit test as a ground truth is both expensive and so limited. So any idea on how to fix it?
Yeah, thanks for the question. So we have tried fuzzing as well. So basically, we can construct fuzzing tests on the Rust side. But the problem is that the imperfect example generated by the fuzzer is of less quality than the example come from the unit test. And we also have some previous work try formal methods and by using model checker and all that stuff. But the question is that they don't scale up to the level of say 10,000 lines of code. So currently, we found unit test being our best option. But we're also exploring by using say like better fuzzer or stuff like that.
Okay, let's thank our speaker one last time. Okay, so our next talk will be a recorded talk by Shangwei Wang from North Carolina State. He will be available on Discord after the talk to answer some questions. So we'll get that on the screen shortly.
By the fact that the input adaptive organization is important for many fields. For example, in the serverless computing area, they have a job controller to assign jobs to different computing resources. For a certain program, different inputs need different resources and take different costs. Input adaptive approach will get the job controller to save resource usage and cost. From our experiments, we noticed nearly 65% resource reduction compared to input oblivious approach. Input adaptive organization are also helpful in other fields. Previous research showed that input adaptive approach can bring 10% to 26% speed up for just the intent collation, achieve 1.5 to 2.5 times performance improvement if liking the more suitable garbage collection based on inputs, and up to 1.47 times speed up on a set of GPU applications. In the previous work, the researchers proposed a three-step workflow for input adaptive optimization. In first step, it needs to extract the important features from program inputs. In second step, it builds the machine learning model from those features to predict the program behaviors. Finally, it adopts model for different optimization targets. The inputs to the program include the satellite images, data collected by weather balance, various ocean data, and so on. It is hard to directly tell what parts or attributes of the input critically affect the speed of the program by only paying attention on the inputs themselves. This is because the significance of each type of inputs are decided by how they are used in the program. Therefore, to analyze the effect of the input, we need to focus on the program. Input characterizations is hence a program analysis problem. Previous work tries to give a systematic solution by analyzing statistical correlations among program behaviors. It needs to collect a set of inputs for a program and test the instrumented program with these inputs under several runs. Through this process, the instruments collect massive profiling logs for many program behaviors, such as the conditions and loop trip counts. Then they did a statistical correlation analysis on these program behaviors to obtain a single behavior, which are defined as behaviors in a program that is strongly correlated with many other behaviors in the program, and meanwhile expose their values early in typical executions. They will be used as the representatives of input features for the program. However, this approach still has some challenges. It is tedious and time-consuming due to detailed profiling runs and extensive correlations. For a program, it may take 4 to 404 hours to gain those data. Therefore, it is hard to be integrated into compiler workflow. By analyzing the prompts and the counts of large language model and compiler, we think it is a promising future to combine large language model and compiler together to solving the limitations we mentioned before. Most notable is that large language model can capture high-level code semantics but faces scalability limitations when it was used to deal with large code bases and give reliable code. We mentioned that large language model has behaviors of almost all pieces of the program. The behavior complexity grows as program code size increases. Our strategy is to reduce the focus of analysis from all pieces to a much smaller set of behaviors, named the similar behaviors, and then map similar behaviors to input features. Similar behaviors are a concept introduced in previous work. The second dimension is code size. We all know that the current large model have a limit on the maximum number of tokens for request. Even the limit becomes larger and larger. Large language models still show poor performance on long context. Thus, it is meaningful to instruct large language models to focus on a certain scope when we try to use it on a program analysis. Our strategy is to use code graph to get a large model to conduct similar behavior analysis on one function at a time. This is the overview of our Maverick design. It has 3 parts. The first part is the preparation process.
Okay, source code info, code graph, represent function code relationship, auxiliary info, codes for each function, recursive cycles in program, global variables in program, macro, return flags, whether a function has return or not. Reductive scheme, choose the right prompt template from creator, generated prompts, and then processor, instruction model creator.
To prepare the inputs for the subsequent analysis. The second part is the RCL code analyzer. It follows a reductive algorithm and a set of well-crafted prompt templates to enable large language analysis through the code graph. And the final part is an extraction model creator, which creates a code script to extract new features from the new inputs. To help you understand what is going on in the RCL code analyzer, I show part of the running example here. The entire example is in the paper for you to read. We are dealing with a function underneath named power. This is the power function. We provide the info side of this function to the large language model. It responds to analyze results, including similar behaviors and input influence. The input influence of this function is none because this function doesn't use input from the entire program directly. This analyzed result is added to the info side of its caller function. And since its caller function only has one callee, that caller function is ready to be processed. So it is added to the process queue. One case inside is we need to carefully design the propagation between the functions. We represent the information passed from the callee to the caller in the analyze results. It includes 3 parts. The first part is single behaviors with auxiliary information. This information includes the reason. The reason is why to choose the variable or program behavior as single behaviors. And another part is position. It means where these program behaviors are. For a function, the single behaviors might be in the function parameters. Maybe it comes from a global variables, or it's just local variables inside this function. The second part is input influence. It includes the order of input reading and what is the program input influence to the values in the function. These pieces of information is to record how program inputs take effect directly on the program, and it will be used for input mapping in the further analysis. The third part is the return value. It records how the return variables get its values. We store this information to avoid the behaviors during the analysis process. But to help large model in that process, we embed some generic instructions in the prompt. One is of the response. This does the single behavior analysis as usual, and then map the single or preserved with the help of a large model. This work we use XGBoost because it is light, scalable, and performance of large models. We employ several prompt engineering techniques to do with the token limit for the large models. We use GPT-4 and GPT-6 inputs for each of the programs. During the detection, we try to ensure that the inputs are typical 33% higher SLO hit rates and 65% resource reductions. The SLO on shortest job first scheduling input adapt can achieve 7 times speed up close to using the true chain. For our conclusion, we think first we propose the first known exploration on leveraging large models to clear barriers for identify critical input features for input-centric program optimizations. we combine large language model with a lower reductive
Okay.
scheme.
I just now realized that
One next time before we move to the next.
this was not actually one of the videos that I wanted to watch, but that's fine. I think I was going to watch this here, not this. Anyway, we'll actually call it a night. It's getting late. Gotta be up early tomorrow. At least that's the plan. Get back to my workouts, my morning workouts. Yeah. I was gonna say I should be back tomorrow evening, but we'll see. I'm not gonna make that promise. Yeah. So if, excuse me. Sorry. Yeah, I'll see you guys around, and if any of this was useful or interesting, please do like and subscribe, and I'll see you around. Have a good night.